Bismillah ar-Rahman ar-Rahim. Now we will discuss few examples on the effect of electric field on charges. This question, which is old exam problem, says an electron traveling with an initial velocity of 10 to the power 5 in the positive x direction, meter per second, enters a region of uniform electric field. So its speed before entering the region was 10 to the power 5 in the positive x direction, and it enters a region of uniform electric field given by E equals 4 times 10 to the power 3 in the positive x direction also. Determine the time it takes for the electron to come to rest momentarily. Okay, so let us make a simple drawing here. This is the electric field. It is pointing in the positive x direction, and it has a magnitude of 4 times 10 to the power 3 Newton per Newton per coulomb. This is the electric field, and it is uniform electric field. And this electron is coming with some initial velocity. So this is the electron. So V0. And it is given V0 is 10 to the power 5 meter per second in the positive x direction. As a result, what will happen to this electron? It will experience a force, and that force is directed opposite to the electric field. So the force is in this direction. So this is F electric. The electric force on the electron will be opposite to the direction of the electric field. If it was a proton, if it is a positive charge, the positive charge will be affected by a force in the same direction as the electric field. But now we have electron. Okay, so as a result, this electron will decelerate. Okay, so it has large speed, 100,000 meter per second. It will decelerate, slow down until it reaches a speed of 0. Then it will reverse the direction. So here at this point, this will be V final equals 0. He's asking about what is the time needed for the electron to come from this initial velocity, 100,000, to that final velocity, which is 0. And it will be momentarily because it will stop for a short time, then it will reverse direction. Similar to this type of motion, the object is moving, it will reach to a maximum height, then it will reverse its direction of motion. Okay, so we can apply Newton's second law. We have F net equals ma, but this will be the mass of the electron. What is the net force on the electron in this case? It will be the charge of the electron multiplied by the magnitude of the electric field, and the direction, of course, will be to the left. This is equal to mass of the electron multiplied by the acceleration. So how much is the acceleration of our electron? It is the charge of the electron multiplied by the magnitude of the electric field divided by the mass of the electron. Okay, so in magnitude, this will be, what is the charge of the electron, my son? It is 1.6 10 to the minus 19 multiplied by the magnitude of the electric field, which is 4 times 10 to the power 3 divided by the mass of the electron. You might wonder, how can I know the mass of the electron? It will be provided to you in the formula sheet. So this is 9.11 10 to the minus 31 kilograms. And if you do this calculation, you will get how much is the acceleration. It is 7 times 10 to the power 14. 7 times 10 to the power 14 meter per second square. Okay, if we know the acceleration, we know V0. So V0 is, what is it for? It is 10 to the power 5 meter per second. Okay, V final, it will stop. So V final is 0. He's asking for the time, and he gave you that the acceleration, which we have just calculated, it is 7 times 10 to the power 14 meter per second square. But notice one thing, that this acceleration is to the left, so it is deceleration. And the initial velocity is to the right, so the acceleration is negative because it is deceleration. Okay, if you remember the kinematics, physics 101, we can use equation number 2 to find what is the time. So use equation 2 of kinematics, which says that V final equals V initial plus AT. Okay, V final is 0 because the object or the electron will stop momentarily. So, and this acceleration is negative. So we'll end up with time equals V initial divided by the acceleration. And if you do this correctly, you will get 10 to the power 5. We called it here V0, no problem. This is V0. 10 to the power 5 divided by the acceleration, which is 7 times 10 to the power 14. As you can notice, it is very small time. It will take 0.14, 10 to the minus 9. 0.14, 10 to the minus 9 second, or we can write it as 0.14 nanosecond. Very quickly, it will come to stop. Let me extend this problem. The problem is solved. So this is the answer of the old exam problem. If he asks us to find what is the distance the electron will travel before coming to a stop, what is the distance between here and there? Would like to know how much is this delta x. Okay, find. This is extra problem, my son. I hope you are following. Find delta x needed for the electron to stop or traveled by the electron inside the electric field. So we can write our given information. We know that V0 is 10 to the power 5 meter per second, and we have V final is 0, and the acceleration is given to be minus 7 10 to the power 14 meter per second square, and we are interested in finding delta x. So here we can use equation number 3 of kinematics. Use equation 3 of kinematics, physics 101, which says that V final square minus V0 squared equals 2a delta x. Okay, 2a delta x, but this acceleration is negative, okay, and this is 0. So the minus sign here will cancel with that minus sign, and we are left with delta x equals V0 squared divided by 2a. If you do the calculations correctly, you will get delta x to be 7.14 micrometer. 7.14, 10 to the minus 6 meter, which is 7.14 micrometer. So I think this question gives us a quick review for kinematics of charged particles in one dimension when it moves in a uniform external electric field. Thank you. This is another example on the effect of electric field on charged particles. We have a charged particle of mass 2.5 gram, as you can see it here. It has a charge of plus 5 millicoulomb, or 5 10 to the minus 3 coulomb, has a velocity initially, which is 25 meter per second. This is the initial velocity in the positive x direction, as you can see. So this is V0 of our particle initially. When it first enters a region where the electric field is uniform and is directed in the positive y direction, as you can see, and has a magnitude 4.9 Newton per coulomb. Okay, as shown in the figure, what is the speed of the particle 2 seconds after it enters this region? Okay, we want to find what is the speed after 2 seconds from entering this region. Okay, so let us try to draw the forces acting on our charge. So this is our charge, okay, and it is positive charge. There is electric field. The electric field is upward like this. So this is the electric field. And it is positive charge. So what will be the electric force on this charged particle? Okay, it is upward, of course, because the positive charge will be accelerated in the positive direction of the electric field. Okay, so this is the force electric. This is the electric force. It will be in this direction. Okay, and because this particle has large mass, it is 2.5 gram. 2.5 gram, which is quite a reasonable mass. If you compare it to the mass of the electron, the previous example, which was example number 1, my son, the electron has a very, very small mass, which is 10 to the minus 31. If you remember, in the previous example, I didn't talk about the gravitational force, because the gravitational force will be negligible when we compare it with the electric force. But now we cannot neglect the gravitational force. So there is gravitational force downward here. This is mg. Okay, if we know the acceleration, then we can decide about the final speed which he's asking about. Okay, so in this problem we say F net along x. Is there any force along x-axis? No force along x-axis. It is moving along the x-axis, but there is no force along the x-axis, so this is equal to 0. Okay, F net along the y-axis, this will give us the mass multiplied by the acceleration along the y-axis. What are the forces along the y-axis? I have Fe upward, and we have mg downward, the gravitational force downward. So I can write that Fe, but Fe is nothing but QE. Okay, so this will be QE minus mg. All of this is equal to may, the acceleration along the y direction. And the mass appearing here is the mass of our particle, which is 2.5 gram. Let us see how much is the acceleration along the y-axis. This will be QE minus mg divided by the mass of our particle. If we do these calculations, let's see. The charge is 5 times 10 to the minus 3 coulomb multiplied by the electric field, which is 4.9 Newton per coulomb, minus the mass, which is 2.5, but this is grams, my son, 2.5 grams. So this is 10 to the minus 3 to convert it to kilograms, multiplied by g, the well-known constant, which is 9.8 meter per second square, divided by the mass, which is 2.5 times 10 to the minus 3. If you do this calculation, you'll find that this number is exactly equal to that number, and the answer will be 0. So what is the acceleration of this particle? There is no acceleration along the x-axis, and there is no acceleration along the y-axis. Okay, so acceleration of the particle has two components, ax, which is equal to 0, ay, which is also equal to 0, so a is equal to 0. So this implies that v final, which is equal to v initial or v0 plus at, but a is 0. Okay, so we'll end up telling that v final equals v0. Okay, so the final answer will be final speed. What is the final speed after 2 seconds? It will be the same as the initial, which was 25 meter per second. And it will be in the same direction also, because there is no acceleration neither on the y-axis nor in the x-axis. So it will be also along the positive x-axis. I hope you understand this question. Let me try to make it more challenging and more exciting for you, my son. Let me replace this particle with an electron. Okay? I am done with this problem. Okay? But I'll replace this heavy particle, which was 2.5 gram, object, I replace it with an electron. What is the mass of the electron? It is 9.1110 to the minus 31 kilograms. Very, very light particle. Okay? And let us see the problem now. You have an electron with a velocity 2.5 10 to the power 6 meter per second, moving in the positive x direction. When it first enters a region where the electric field, the same electric field in the previous problem, in the positive y direction as shown in that figure, what is the speed of the particle 2 microseconds after it enters this region? Okay? So, for the electron, I am still in example number 2, but modified version of it. We made slight modification. So this is the electron. This is electron. And we have the electric field is upward. This is the electric field. It is uniform electric field and it is upward. It has a magnitude of 4.9 Newton per coulomb, 4.9 Newton per coulomb, and this is the electron. What is the force on the electron in this case? The force on the electron will be opposite to the direction of the electric field. So the electric force is this way. How much is this F electric? It is equal to Q, which is the charge of the electron multiplied by the electric field. Somebody will tell me now that where is the gravitational force? Can we or should we consider the gravitational force? What is the gravitational force in this case? Let me calculate by the side. Gravitational force Fg in this case for the electron will be the mass of the electron multiplied by G, which is 9.8. So you are talking about 9.11 10 to the minus 31 multiplied by 9.8 or 10, for example. So this is roughly 9.11 10 to the minus 30 Newton. It is very, very small force if we compare it with the electric force here. Okay, so the electric force is how much in this case? It is Q, which is 1.6 10 to the minus 19 multiplied by this 4.9. So this is something multiplied by 10 to the minus 19. This is the force in newtons. And here we have the gravitational force, which is 10 to the minus 30. So we have an 10 to the power 11 times less than this force. Okay, so this is negligible. Negligible. We should neglect, or we shouldn't worry about the gravitational force because it is negligible when compared to the electric force. I hope you understand what I am telling you, my son. So the only force here is the electric force. Okay, and this is the original or V0. So V0 was in this direction, and now we have to tell that F net along X is equal to, yes, tell me, my son, what is the net force along the X-axis? Yes, you are right. There is no force along the X-axis, so this is 0. So this implies that the acceleration along X is equal to 0. What about the acceleration along Y? So F net along Y will be equal to mass of the electron multiplied by AY, the acceleration along Y-axis. But what is the force along the Y-axis? It is only the electric force where the gravitational force is negligible. Okay, so this is QE equals mass of the electron AY. So AY is QE divided by the mass of the electron. If you do this calculation, you will get the acceleration of the electron to be, of course, this is 1.6 10 to the minus 19. This is 4.9. This is the mass of the electron, 9.11 10 to the minus 31. If you do the calculations correctly, this is 8.6 times 10 to the power 11 meter per second square. It's very large acceleration. as you can see. And it is directed in which direction? It is here, downward, okay? In the negative y. In the negative y axis. Because the negative charge will accelerate opposite to the direction of the applied electric field. Okay, so what is V final, if we would like to find, what is the final speed of the electron after this amount of time, which is 2 microseconds. To do it, what is V final x? V final x will be V0x plus AXT, but AX is equal to 0, so this will be the same as the initial speed, and the initial speed is 2.5, 10 to the power 6 meter per second. What is V final y? V final y will be V0y, okay, minus, because now it is moving downward, okay, and the acceleration is in the negative y-axis, so this is minus AY multiplied by the time. What is V0y? Initially, the electron was moving in the positive x direction, so the y component of its initial velocity is equal to 0, if you remember from physics 101. So V final y will be minus this acceleration multiplied by that time, which is 2 times 10 to the minus 6, and this will give us the final to be 1.7 10 to the power 6 meter per second, okay, and this is negative, meaning that it is in the negative y direction. If you want to find the speed, so the velocity, I can write it, V final equals 2.5 10 to the power 6 in the positive I minus 1.7 10 to the power 6 in the, okay, negative j, and all of this is given in units of meter per second. So the speed in that case, V final, will be the magnitude of this velocity, square root of 2.5 squared plus V 1.7 10 to the power 6 squared, so here squared, V final y squared, and if you do this calculation, you will get the final speed to be 3 times 10 to the power 6 meter per second. Now, we had 2 cases for this problem. In one of them, we consider the gravitational force, okay, because it has appreciable mass, and there is appreciable comparison between the electric force and the gravitational force. And the second example was for the electron, where the electric force was very large when compared with the gravitational force, which we have neglected, and we worked out this problem without considering the gravitational force. Thank you. This is another example about the effect of electric field on charged particles. Here we have electric field, which is uniform, as you can see. It is 100,000 directed in the positive x direction, causes the 5 gram point charge. So here the mass of our particle is 5 gram, pointing as in the figure, and it is in equilibrium. It doesn't move up nor down, it is just still sitting there, and that angle at which the equilibrium takes place is 20 degrees with the vertical. What is the charge on the ball? Okay, so let me redraw the situation. So this is the ceiling, and here we have a string, and this is our charged particle, and the angle between the string and the vertical is equal to 20 degrees. Okay, so if we would like to, this is the electric field, and we would like to draw the free body diagram. What are the forces acting on this charged particle? Okay, we know that it has a mass which is 5 gram, okay, and it is affected by Fg, gravitational force. So we have Fg equals mg in this direction, and there is a tension in this string, so there is tension here. What else? Of course, because it is a charged particle, there is electric force on it. And we can notice that the electric force is pulling it in the direction of the electric field. So the force F electric is to the right, okay, and this is how much? This is QE, okay? What can we say about the type of this charge? This is a charge which is accelerating along the direction of the electric field. So what does it mean? It means that this charge is positive. So this implies that Q should be positive charge. If it was negative, my son, so let me write here positive, so this is positive. If it was negative, and we do the same experiment with a negative charge, let me draw it, the negative charge will accelerate opposite to the direction of the electric field. So the negative charge, if it was negative, the figure will look like this. So the electric force will be in this direction, so this will be F electric QE, okay, and here we'll have mg, and there we'll have the tension, okay, because the electric field is to the right and the particle is accelerated to the left, or being affected by electric force which is to the left, so in that case it will be negative. But this is not our case now. Huh? I was just trying to explain another situation and to expand your knowledge. Huh? So Q should be positive, and very important point here is that this particle is at rest in equilibrium, meaning that the net force on it should be equal to 0. So F net should be equal to 0 along X, and also F net along Y should be equal to 0. Why did I say this? Because it is in equilibrium. But what are the forces along the X? This force is along the X, this is along the negative Y, but this tension is neither on X nor Y. I have to analyze this tension into two components. One component along the positive X here, the positive Y, and another component which is along the negative X. Okay, if that was 20 degrees, this is 20 degrees as well. Okay, so here we'll have T, this component is T cosine 20, and this will be T sine 20, okay, which is that one. So this is opposite to the 20, opposite gets sine, and here this component is the neighbor or the adjacent of this angle, so it will take the cosine. T cosine 20, this is T sine 20. So here, F net along X equals 0 will give us that T sine 20 or QE to the right minus T sine 20 equals 0, or this is equal T sine 20. Okay, along the y-axis we have these two forces, T cosine 20 equals mg. Okay, so I can divide these two equations, just divide, this is 1, this is 2. If you divide 1 divided by 2, this will give us divide 1 over 2. This will lead to the following. We'll have T will cancel out, sine 20 over cosine 20, this will give us tan 20 equals QE divided by mg. And he's asking us about the magnitude of the charge. Okay, so the charge will be mg tan 20 divided by the magnitude of the electric field. If you do these, plug in these numbers correctly, you will get the following. What is the mass of the particle? It is 5 grams. You have to convert it to SI units, kilograms. So this is 510 to the minus 3 kilograms times G, which is 9.8 meter per second square, times tan 20 divided by the electric field magnitude of that, which is 100,000 or 10 to the power 5 Newton per column. The answer for this will turn out to be 178 times 10 to the minus 9 coulomb, or simply we can write this is 178 nano coulomb, and we said at the beginning that it is positive, so this is positive charge. So the charge on our particle here is positive, and it has a magnitude of 178 nano coulomb. Thank you. This is another example, but here we have a dipole. What is the effect of electric field on a dipole? Pointed charges Q1 plus 5 microcoulomb and Q2, it has the same magnitude but opposite sign, minus 5 microcoulomb, are separated by 5 millimeter. Okay, so this is a dipole. What is Q of the dipole? It is 5 microcoulomb. What is D, which is the separation between the two charges, is 5 millimeter. Forming an electric dipole, the charges are placed in a uniform electric field whose direction, so the direction of the electric field makes an angle of 40 degrees with the line connecting the charges, which is the dipole. So the charge between the dipole moment and the electric field is given to be 40 degrees. What is the magnitude of this field if the torque at that instant exerted on the dipole has a magnitude of 7.5 10 to the minus 9 Newton meter? Let me give you a simple drawing. This is the electric field. Let us assume it is in this direction. It is uniform electric field. Okay? And we know the magnitude. No, he's asking about the magnitude of the electric field. Okay, so the magnitude of it is unknown. And we have a dipole. And the dipole is like this. We have a negative charge here, positive charge there. Okay, and this is P is going in this direction from positive to negative, and this is the electric field. And he told us in this problem that this line joining the two charges making an angle of 40 degrees with the electric field. Okay, he gave us a Q equals 5 microcoulomb, and D, the separation between the two charges, which is 5 millimeter, and he is giving me that at this moment the torque equals, it has a magnitude of 7.5 times 10 to the minus 9 Newton meter. This is the torque. And he is asking us to find how much is the electric field if you know, or if you are given this information. The formula we derived earlier for the torque equals P cross E. It is the cross product between the dipole moment and the electric field. Okay? So if we would like to find what is the magnitude of this torque, the magnitude of the torque equals magnitude of the dipole moment multiplied by the magnitude of the electric field multiplied by sine the angle between them. Let me call it sine phi, and this angle in this case will be 40. Okay? So what is the magnitude of the torque? Magnitude of the torque is given to us. This is unknown. Magnitude of the electric field unknown. Sine theta or sine phi is sine 40. Okay? What is the magnitude of P? Magnitude of P we have discussed earlier. It is just the QD. So we'll end up with magnitude of the torque equals QD. Okay? Everything is positive here. Q is positive, D is positive, multiplied by the magnitude of the electric field multiplied by sine phi, which is sine 40. Okay, so I can write that E, the magnitude of the electric field, from this given information equals the magnitude of the torque divided by QD sine 40. Okay, plugging in the numbers, we will get the torque is 7.5 10 to the minus 9 SI units, Newton meter, divided by Q, which is 5 micro. So I should replace the micro with 10 to the minus 6. Okay, multiplied by D, which is 5 millimeter, so I should replace it with 5, 10 to the minus 3 meter, multiplied by sine 40. Okay? So this is 10 to the minus 9, we'll cancel with this, 10 to the minus 9. And we are left with the magnitude of the electric field, which is 0.47 Newton per Coulomb. You should know that this torque is having this magnitude for this situation only. If the angle is different, we'll have different value of the torque. So the torque will be different for different orientation of our dipole. Thank you. This is another example related to the effect of electric field on electric dipole. How much work is done by an external agent to turn an electric dipole by an angle of 20 degrees in a uniform electric field of this magnitude, 700 Newton per Coulomb, and it is uniform. If the dipole moment has a magnitude of this much, so he gave you the product of Q and D, which is the dipole moment. This is given by 4 10 to the minus 9 Coulomb meter. And the initial angle was 0 degree. Let me explain this problem in drawing. Okay, so we have electric field. This is the electric field. Okay, it is uniform electric field, E, and he gives us the magnitude of the electric field. It has a magnitude of 700 Newton per Coulomb. So initially, our dipole was like this, was at an angle 0 with the electric field. So this is the negative charge, and here we have the positive charge, okay, and they are separated by distance D, and this is Q, this is minus Q. This is the dipole initially. The initial angle, this is initially, okay. Finally, he told us, finally it will be making an angle of 20 degrees with the electric field. So it looks finally like this. It will be like this. We turn it by applying a force. So an external agent will apply a force to have this dipole making an angle of, so this is the plus Q, this is the minus Q, and the distance between them is D, and the angle now is how much? Is 20. This is finally 20 degrees. Okay? He is asking us find the work done by external agent, or the work applied by an external agent is equal to how much? Okay? We know that the work applied is equal to, if you remember my son in our discussion, that from work kinetic energy theorem tells us that work net equals the change in the kinetic energy. Okay? And the work net is the work done by the conservative force plus the work done by non-conservative force. Now I call it work applied. Okay? And this is equal to delta K. Then if delta K equals 0, because we brought our dipole from this position, so initially it has 0 kinetic energy, and finally we fix it at this position, so the final kinetic energy is equal to 0. So delta K is 0 in this case. What do you notice? The relationship between the work done by the electric field and the work applied, it will be of opposite sign. So work applied will be equal to minus the work done by the electric field, which is conservative force in that case. Okay, so minus, but we know that the work done by a conservative force is minus the change in the potential energy. Okay, so minus minus, this will lead to delta U. So the work done by the applied force or the external agent will be the change in the potential energy. So this is nothing but U final minus U initial. We want to know what was the initial potential energy, what is the final potential energy. This is the final. I forgot to write the word final here. This is finally. Okay, this is initial situation. That is the final situation. What is U initial and what is U final? Find the difference between them. You will get the work done by the external agent. So, from our discussion, we came to the conclusion that U equals minus P dot E, the dot product between the electric dipole moment and the electric field. Okay? And this is minus sign. So U initial equals how much? U initial. I have drawn U initial with red color. Let me do it with red. So initial situation, U initial equals, I have a minus sign, okay? P is given to us. It has this magnitude, so it is P multiplied by E, which is the magnitude of the electric field, okay? Multiplied by the electric field, multiplied by cosine, the angle between them. But initially, the angle between them is 0, okay? So we will end up with the following, minus P, which is 4 10 to the minus 9, multiplied by the electric field, which is 700, multiplied by cosine 0, which is 1. This will lead us to minus, U initial is minus 2.8 10 to the minus 6, and the unit is joule. Okay, this is the initial potential energy when the angle was 0. Okay, for final situation, I have drawn it in green. So U final will apply the same formula, minus P E magnitude, okay, cosine the angle between them, which is 20 in this case. So this will be cosine 20. If you plug in the numbers, same P, same E, but now I multiply it with cosine 20, you will end up with a minus minus 2.63, minus 2.63 times 10 to the minus 6 joules. Okay, now I am ready. I want to find what is the work applied. Work applied, I come here, work applied will be the difference. I start with U final minus U initial. U final minus U initial. And you will end up with, this is more negative than this, huh? So you will end up with a positive value, and that will be 1.7 10 to the minus 7. 1.7 10 to the minus 7 joule. This is the work done by the applied force. I think it is it clear, my son? If I ask you, let me extend the question. This is the answer, okay? I am done. But let me ask you extra question. Find how much work, the same problem, but how much is the work done by the electric field. So he's asking us for the same situation. Initially it was 0 degree, finally it is 20 degree. Okay, I was asking about the work done by external force. Now I am asking about the work done by the electric field. The electric field is the conservative force. So the work done by conservative force will be minus the work done by the applied. Okay, so this WC will be minus delta U. So it will be U initial minus U final. As you can see, this will be negative and it will have the same magnitude, 1.7 10 to the minus 7 joules. Thank you.